Hello everyone, thank you for being here. My name is Rachel Blin and I'm a PhD student from the Lidar laboratory in France. Today I will be presenting a new RGB and polarimetric multimodal dataset for road scene analysis in adverse weather conditions. Before going into further details regarding the dataset, I will give a few words about the different topics of this work. As we all know, providing an accurate road scene analysis is a vital task when it comes to autonomous driving. As a matter of fact, a mistake could lead to serious consequences, implying humans' life. Nowadays, autonomous driving has shown great performances, especially thanks to the deployment of deep learning those past few years. However, some improvements are left to be done when it comes to adverse weather conditions because the visibility is altered. Some recent work have shown that adding non-conventional sensors could improve the road scene analysis in such situations. In this work, we will use polarimetric imaging to analyze road scenes because it characterizes an object not only by its color or shape, but by its reflection, which is invariant under strong reflection or poor illuminations. As we can see on the slide, on the bottom right in the middle and on the right we have the polarimetric features of the ruler, enabling to see other properties of the object. Now that I introduced the different topics of this work, I will speak about our motivations before giving more details about the polarities dataset. I will also explain the experiments carried out in this work before concluding the presentation. Previous work have demonstrated that the fusion of polarimetric features with RGB ones using a deformable parts model detector improved cars detection. More recently, we showed in our previous work that after training two networks on respectively ANPER RGB and polarimetric datasets, car and person detection was improved in foggy weather conditions. In this work, it was primordial to release the first multimodal paired RGB and polarimetric dataset for road scene analysis in adverse weather conditions in order to reproduce and confirm these results. Before giving details regarding the polarities dataset, it is important to introduce the polarization formalism. When an incident light is being reflected by an object, it becomes partially polarized. A polarizer rotated at an angle alpha is placed in front of the sensor, enabling to capture the amount of linearly polarized light at this specific angle, which we call the intensity. In this work, the PolarCam 4D technology was used, which enables to provide four intensity I0, I45, I90, I135 corresponding to the rotation angles of the polarizer 0, 45, 90 and 135 degrees. From these obtained four intensities, we can compute the Stokes parameters. The first element S0 is always strictly positive and represents the total intensity of the scene. S1 and S2 represent respectively the amount of horizontally or vertically polarized light and the amount of light polarized at plus or minus 45 degrees. The second block represents the formula that links the intensities and the Stokes parameters. From the Stokes vector, we can compute other polarimetric features. The first one is the angle of polarization, which is the orientation of the polarized part of the wave with regards to the incident plane. The second one is the degree of polarization, which refers to the quantity of polarized light in the wave. Now that we have all the needed polarimetric background, I will introduce the polarities dataset. Regarding the data acquisitions for the training sets, The polarimetric and the RGB cameras were placed behind the windshield at the height of the driver's eyes, and the scenes were captured under good weather conditions. As for the testing sets, the polarimetric and the RGB cameras were placed outdoors at the height of the driver's eyes, and the scenes were captured under foggy weather conditions. Some examples of the dataset are displayed on the slide. The first row represents the intensities I0s of the polarimetric images, and the second row represents the RGB equivalent of the scenes. The dataset can be downloaded at the following link. As for the dataset properties, they are summarized up in this table. As we can see, the training set is constituted of 1,640 images in each modality, the validation set of 420 images in each modality, and the testing set of 509 images of each modality. We choose to label 4 classes in our dataset, which are car, person, bike, and motorbike. Because our dataset doesn't contain enough images to train a deep neural network from scratch, in order to be able to use a pre-trained network for the training process, it was important to constitute 3 channels images from polarimetric features. We came up with 5 data formats, which are the stocks images, the Poincaré images, the HSV images, the Pauli-inspired images, and the intensities images. On this slide, you'll find an illustration of each of these data formats of the same scene. This table summarizes up the polarimetric features contained in each channel of the polarimetric data formats. For example, for the intensities images, we have the 3 intensities I0, I45, and I90 respectively placed as the RGB configuration. Now that I presented the polarities dataset, I will speak about the experiments carried out in this work. We used a RetinaNet network using a ResNet 50 backbone pre-trained on the MS COCO dataset as a basis for all of our experiments. A network was trained separately on each data format containing road scenes under sunny or cloudy weather conditions, and was tested on the same data format containing road scenes in foggy weather conditions. The results of this experiment are shown in this table. In blue, we have the detection results provided by the RGB training, and in bold, we have all the detection results of polarimetric data that overcome it. As we can see, the mean average precision of the intensities images, the stocks images, and the Pauli-inspired images is superior to the one of the RGB images. Here you have an illustration of the detection results in each of the data formats of the same scene. From left to right and from top to bottom, you have the RGB images, the intensities images, the stocks images, the Pauli-inspired images, the HSV images, and the Poincaré images. We can notice that the detection results provided by the intensities images, the stocks images, and the Pauli-inspired images are better than the one provided by the RGB images. To conclude this presentation, I introduced in this work the polarities dataset, which is a multimodal RGB and polarimetric dataset of road scenes, including adverse weather conditions. This dataset demonstrated that polarimetric object detection overcomes RGB object detection in adverse weather conditions. In future work, we plan to extend this dataset to other adverse weather situations such as rain or snow. We also plan to find a convenient fusion scheme for RGB and polarimetric features in order to get the best of each of these 2 modalities to improve even more object detection in such situations. Thank you for your attention. I am now ready to answer your questions if you have any.